We have spent the last 3 weeks looking at projectile motion. In the picture above, we have an angled launch at some angle above the ground. We're going to make some assumptions here. We're leaving from the ground. There are no forces except gravity, and our projectile is going to land back on the ground. So we wind up getting a symmetric, parabolic trajectory, something we've looked at over and over again. Now, what's pretty interesting is you can take the motion that we've looked at in both the horizontal and vertical direction, and we can create equations that allow us to find the launch velocity, range, and angle of launch in terms of the others. All right. So what you're going to see here is a derivation. There are no numbers. We are just working with our equations and seeing how they work hand in hand. All right. Now, in all our problems, we have always broken up our initial velocity, right, our total velocity, into both the sideways piece, right, we're calling Vx here, see it's blue, and also our initial y velocity, here denoted by red. Notice I put an I here because the velocity in the y direction changes throughout the path. So when we do the hypotenuse, the total velocity times the cosine of theta, that gives us our sideways speed. And when we take the total velocity times the sine of our launch angle, we get the initial vertical velocity. Right? In all these problems, we've had to figure out the time to the peak as well as the total time of the trajectory. And what forces that time to the peak is gravity, right? If we have been working in meters per second squared, we've been rounding it to 10, but it's actually negative 9.8 meters per second squared. In English, it's negative 32 feet per second squared, right? Now, in order to figure out that time to the peak, gravity takes away this vertical velocity at this rate. So if you look at the definition of acceleration, right? Here I'm using g for acceleration due to gravity. That's going to be equal to our change in vertical velocity, right? The final y velocity minus the initial one divided by time, right? Now, the special thing about the peak is that the y velocity is 0. So if we were to plug in 0 here for VFY, right, we would get an expression for the time to the peak. And it would wind up being negative of the initial vertical velocity divided by that acceleration due to gravity. Notice what we did over and over again. If we had, say, a launch speed of 40, we just did 40 divided by 10 and we get 4 seconds to the peak. So this expression right here represents what we've been doing for the last 2 weeks. Now, to get the total time of the path, right, because it's symmetric and we're landing back down on the ground, the total time in the air just winds up being twice as much. Right? So if we had a problem where this was 4 seconds, all we did was double it, and we got the total time in the air. Right? So now we have some expressions without numbers in them that explains the projectile motion that we've been looking at recently. Right? Now, don't want to show you all that at once. All right? So in projectile motion, we have calculated the range, right, which is the distance that the projectile travels in the sideways direction. We have taken the constant forward speed and multiplied it by the total time in the air. Well, now we have expressions for these two things, and we're just going to algebraically substitute them, right? Our sideways speed winds up being our total speed multiplied by the cosine of the launch angle. But our total time in the air now is represented by this expression, which was just on the previous page. Okay? We can continue to go further here because we can write the initial vertical velocity as the total velocity times the sine of our launch angle, right? So we wind up getting this long, involved expression that represents our range. Right? Now, you don't have to understand the proof of this, but there's a thing called a double angle formula, right, in trigonometry, right, which is kind of above us right now. But you can prove that the sine of twice an angle is equal to the product of 2 times the cosine of the angle times the sine of the angle. All right, and notice if you look in this expression, we have a 2, we also have cosine of theta, and we have sine of theta. So if we come back to our expression for range, we can reorganize it. Notice the velocity is in there twice. So v times v is v squared, right? A negative comes out front. And then we have 2 times the cosine of theta times the sine of theta, all right, within it, all divided by the acceleration due to gravity. So we can take this double angle formula relationship and substitute in the sine of 2 theta for this whole thing right here. All right, so if we go to the next line here and drop down, we have simplified our expression for range, and it winds up being the negative of the launch velocity squared multiplied by sine of twice the launch angle, all divided by the acceleration due to gravity. Right? Remember, the acceleration due to gravity is negative. So these two negatives wind up canceling out, which leads to a positive range all the time. Right? What's interesting is if you look at this equation, play around with it a little bit, your sine function is maximum when you put in 90 degrees. And because you have 2 times theta here, you only get that if you launch at a 45-degree angle, which is when we get the greatest range, which we have gone over in previous weeks. Right? That's all the hard work, right? Because once you have this expression for range, right, you can rearrange it, right, to solve for other things, all right? So if we have this expression for range, we can work it around and solve it for launch velocity. So if you were to take this expression and solve for launch velocity, right, you wind up cross-multiplying the range and the acceleration due to gravity, then wind up dividing by the sine of twice the angle, all right? And then you would have to take the square root of all of this, right, in order to get your launch velocity, all right? Technically, I believe, right, there should be a negative in front of all of this. I kind of forgot that, right? So a negative times the acceleration due to gravity, which is also negative, will lead to a positive value underneath the square root sign, so none of the math teachers yell at us. All right. Lastly, you could rearrange this equation one more time and solve, in this case, for the launch angle. This looks a little uglier, all right? In order to get an angle, you have to take an inverse sine, all right? So if you were to, at this point, cross-multiply the range and the acceleration due to gravity, then divide by the velocity squared, a negative comes along here, you would have to take the inverse sine of this expression. That would give you twice the angle. So at the end, you would have to divide that all by 2 to get the launch angle, right, in terms of the range and the launch velocity.